Okay, there we are. Hello, lads and ladies. Welcome back to MAC2311 Honors. Today, we're going to talk a little bit more about derivatives of trig functions. I'm going to show you some neat tricks with those special trig limits from last time. And then we're going to talk about the chain rule. So this is our last lecture before the exam. Let's do it. Or is it? Sorry, let me triple check everything. I guess we should do that too. My brain just basically turned into mush in the last month. That's okay. So let's do the thing. That's right. We have one more lecture after this before the test, right? The test is next Wednesday for you guys. I'm sorry. Didn't mean to scare you. More trig derivatives. And don't panic, the hard work is already done there. I also want to look at some limits that we can calculate kind of as a consequence of all that work we did on Wednesday with the sine theta over theta limit. And after we do that, we will cook up the derivatives of the other trig functions using the product and quotient rules, and then we'll move on to the chain rule. So the section numbers are 3.3 and 3.4 respectively. And just a little reminder, as much for myself as for you, exam 1 is next Wednesday, which is the 29th, right? That's the date we set, 1 week from last class. Check the date. Yeah, next Wednesday, 29th. Okay. And this is in class. The procedures for the exam are not terribly complicated. You'll need to sign into Zoom on your cell phone. So make sure you have Zoom installed on your phone. And then you'll have to put the phone somewhere I can see your desk, your hands, your lap, all that stuff. I really like this top-down view. Some people have been like putting their phone above them, looking down. That's really nice. The off to the side thing is fine also, as long as I can see all those things reasonably well. But we'll talk more about that. Let's get into it, right? So last time, I'm just going to recap the stuff we cooked up last time. We saw that the limit as theta goes to 0 of sine theta over theta is equal to 1. And one thing we're able to get as a consequence of this is the limit theta goes to 0 cos theta minus 1 over theta. This is 0. I call these the special trig limits. Yeah, they're special limits and they're made up of trig functions. So one of the things I'm going to show you today are some consequences of these special trig limits, which are other limits that we can cook up now that previously we would not have been able to calculate. Also, we saw that the derivative of the sine function is the cosine function, and that the derivative of the cosine function is negative sine x. All right, so these were the big results from last time. Yeah, good question, Radha. So originally, right? The way the testing center used to work was, yes, I would send you guys over there and it would be during class time. If you're going to take the test at the testing center right now, because they're so short-staffed, they can't handle a large group coming in at once. They got like 2 people working there right now. So I would be forced to open the testing window up a little bit for those who are going to take it at the center. So if you don't want to deal with my proctoring rules, you can take it at the center. I'll say this though, because they're super short-staffed, if you can take it with me online, that would be preferred. But if it's going to cause any sort of hassle for you, like you might miss a class or be late to another class or anything like that, you're more than welcome to take it at the testing center. Or if you just need that environment, right? If you cannot perform well on a test in the online environment, maybe it's noisy at home or something like that, by all means, send me the message. I'll make a reservation for you at the testing center. We can do that. The test is going to be next Wednesday, right? And we're going to do it in class during class time. So it will be due at the end of that class period. So we saw last time the special trig limits and these basic trig derivatives. The first thing I'd like to do today, probably the most important thing from section 3.3, is to flesh these out, get you the derivatives of the other trig functions, so you've got all 6. Those are not hard. So, ready. I think my wife just crashed the car into the side of the garage. Okay, baby. So here's our theorem. We know that the derivative of sine is cosine. I'm just going to write them all out. And that the derivative of cosine is negative sine x. We saw these last time. The derivative of the tangent function is secant squared of x. The derivative of cotangent is negative cosecant squared of x. The derivative of the secant function is secant x tangent x. And the derivative of the cosecant function is negative cosecant x cotangent x. And you see how I have these arranged in 2 columns? Thinking of them like this is nice, right? Because there's some patterns, right? Compare here with here. The cofunctions all have the same sort of shape derivative as the original functions. You just swap each function for its cofunction and pop out the negatives, like the derivative tangent is secant squared, derivative cotangent is negative cosecant squared, right? But it's like the secant thing, just the co version with a negative out front. Yes, the square in any of these positions over the trig function, like secant squared, is secant x times secant x. Yeah, the square in the middle here means the whole thing squared. It's different from having the square inside. Okay. So the top line we've already proved. the other four, I still need to cook up for you. I think maybe I'll do like this one and let you guys cook up the other two because they're good exercises. And I'll tell you that proving one of these four is a pretty common test question for me on exam 1. Bottom left here says that the derivative d dx of secant x is secant x tangent x. Yeah, I apologize. My secants tend to get a little sloppy because I write them a lot, but SEC, this is a secant x, sorry. Okay, so let's prove some of these. We've already proved. I'll label these rows as like 1, 2, 3. We've already proved both items in row 1. Right, we did those manually using the definition. Now we'll use them to prove the rest. Like I said, I'm not going to do every single one of these because the arguments are a little bit repetitive. But for example, let's take a look at the derivative of the tangent function. Okay. I want to cook up the derivative of the tangent function, but I don't want to write down the limit h to 0 f of x plus h minus f of x. I want to do something else. I want to make my life easier. Does anybody see an easier way to get the derivative of the tangent function, knowing what we know, that the derivative of sine is cosine and the derivative of cosine? Yeah, very good. We're going to start by writing the tangent inside here as sine over cosine. All right, this is the definition of the tangent function for most people. Tangent of x is sine of x over cos of x. Why is that nice? So Daniel's on it. Why is this nice? In what sense do we move on from here?
I feel like we could then we can take it apart. Could we take that apart?
It depends.
Because then we also
take it apart.
Because sorry, go on.
That's okay, that's okay. Yeah, so the other rules we know. What rules? It's true the derivative of sine is cosine, but I can't just say differentiate this and then differentiate that, right? That's not how.
It's technically sine x times 1 over cosine x. Isn't 1 over cosine x equals something else useful?
1 over cosine is secant, yes, but let me first add a little caution here. No, this is not the derivative of the top over the derivative of the bottom. This is maybe the tempting thing to do. Why is that not the case? What's wrong with the purple? It's a reasonable thought, don't get me wrong. I'm not saying that 99% of people wouldn't try this right away. But there's a different kind of rule we need to apply to differentiate expressions like this. This is a fraction, right? This is a quotient. You need the quotient rule. Right, that's the only way we have to differentiate expressions where the top and bottom are both variable. So what we use instead of this, we use the quotient rule, which remember says like f over g, all primes, the derivative of f over g is g times f prime minus f times g prime over g squared. Low d high minus high d low over low low. We use the quotient rule to differentiate this. And the nice thing is that all the other trig functions are quotients of sine and cosine. So we can cook up the derivative of any of these four by rewriting them as sines and cosines. So while this isn't kosher, what is kosher is I write this time as the bottom times the derivative of the top. And I'll use the prime notation here because it's nicer. Minus the top times the derivative of the bottom all over the bottom squared. So this is how we can proceed. This works. So now it's just about cleaning up this numerator. I know what the derivative of sine is, right? And I know what the derivative of cosine is. So the top is cos x times the derivative of sine, which is also cos x, minus sine x times the derivative of cos x, which is negative sine x. And everything here is still divided by cos squared x. Cosine times cosine, that's cos squared x. And then I've got minus sine times negative sine, that's plus sine squared x. This is divided by cos squared x. Now, what do you notice about that numerator? What is cos squared x plus sine squared x?
It's 1, isn't it?
Very good. Yeah, that's your Pythagorean identity.
And then 1 over cosine squared x equals secant squared x.
Exactly. So that numerator is 1. The downstairs is cos squared x. So this is the same as 1 over cos x, 1 over cos x, which is secant x times secant x, which is secant squared x, which is what we wanted to show. So this is the derivative of tangent. Any questions on any one of these steps? So far, this class has not had a lot of trigonometry in it because until now, we really didn't have the machinery to deal with trig, at least not in terms of calculus, right? Taking limits of trig functions can be a bit tricky. And certainly taking derivatives of trig functions until yesterday was impossible for us. But now that we have the product and quotient rules and the derivatives of sine and cosine, we can cook up the derivatives of any of the trig functions as we want. I said I would do one of the other ones. Let's do the cosecant derivative. So just like with tangent, our first step is to rewrite cosecant in terms of sines and cosines. Cosecant, by definition, is 1 over sine. So this is 1 over sine x that I'm differentiating. And that's again going to be a quotient rule thing. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So help me out. What are the pieces here? What is 1 primed? What's the derivative of the constant 1?
0.
0, good. So the numerator is sine x times 0 minus 1 times the derivative of sine x is cos x. All of that is over sine squared x. Now sine x times 0 is 0, so this is negative cos x over sine squared x. And remember what I said. I said the derivative of cosecant is negative cosecant cotangent. Did I lie? Is this cosecant cotangent, or how do we see that?
Could we split that into cosine over sine times 1 over sine x?
Very good. And I'll write the 1 over sine x first to make it look kind of the way we want. So the negative is this negative, and then cosine over sine squared is 1 over sine times cosine over sine, right? That's how fractions multiply. They multiply straight across. And now that is negative cosecant x times cotangent x, right? 1 over sine x is cosecant x. Cos x over sine x is cotangent x. So that's that done. All right, there's 2 more for you to do. The derivative of secant and the derivative of cotangent. They both go exactly the same. Right? So I won't deprive you of discovering those on your own. You should go through that process, right? You should, for yourself, prove the remaining 2. Any questions on these? So definitely understanding these proofs is good, right? They're not terribly hard. They're good ways to introduce the derivatives of trig functions and proof in this setting. But at the end of the day, what you really need to do here is make sure you remember these. You gotta just know these cold. These need to be like boom, 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 really fast. If you prove each of them for yourselves, then you will remember them cold. And the other way you can help to remember these is by solving lots of problems with them. So let's solve 1 or 2 problems. Let's say find f primed of theta, where f of theta is theta sine theta. Right? There we go. F primed of theta here would be what we get by applying the operator d theta to theta times sine theta. What sort of rule am I going to need for this?
Do we for oh, never mind.
Yeah, this is a product. Daniel and Talia in the chat are correct. I've got one thing here times another thing here. Neither of them are constants, right? So I can't just pop the theta out. I need the product rule. Okay, and I'll write it in terms of u's and v's here because we've already got the variable f spoken for. You differentiate the one, leave the other alone, and then add that to what you get when you leave the one alone and differentiate the other. There are, yeah. Most of them involve the chain rule also. So we haven't quite gotten to that, but there's several problems with the trig functions in there. So here, I will differentiate the theta, leave sine theta alone. I'll write it in the prime notations. This is theta primed times sine of theta plus theta times sine of theta prime. The derivative of theta, remember theta is playing the same role here that x usually plays. Don't be intimidated by the different variable we're using. The derivative of theta is 1. And then sine theta is sine theta plus theta times the derivative of sine theta is cos theta. So that's it. This is sine theta plus theta cos theta. I don't know of a mnemonic for the product rule, like the low-d high thing for the quotient rule. The way I think of this is you just differentiate them one at a time and then add them up. So if you've got a big product, this actually generalizes really nicely. If you had like u times v times w all primed, it would be u prime times vw plus u times v prime times w plus uv times w prime. You just differentiate them one at a time and add them up. All right. Let's do one more example here before we talk about the special trig limits. Actually, we got to get into the chain rule too, don't we? Okay, let me just move to the special trig limit stuff. I'll do two parts here. Let's do lim x to 0 tangent x over x and lim t to 0 sine of 3t over 2t. Get that last guy a little more. Hold here for just one more second. Is there any questions on what we're doing here? Where the pieces are coming from? Okay. Let's look at these limits. Just to be clear, we can't get either of these by plugging in 0, right? The tangent of 0 is 0, and here the bottom would be 0. So this is 0 over 0. And the same issue here. Neither of these can be done by direct substitution. What we can do, say for the first guy, is rewrite lim x to 0 tan x over x in terms of sines and cosines. This is lim x to 0 sine x over cos x all divided by x. And then we can clean that up as lim x to 0 sine x over x times cos x. Just, fractions. And then this, no, I can split up into two pieces that are each easy to handle. So I would say this is lim x to 0 sine x over x times 1 over cos x. Because I know what the limit of sine x over x is as x goes to 0. And cosine of x, this doesn't have any weirdness at 0. So if we're being very careful, you could split this up using limit laws and say, okay, this is lim x to 0 sine x over x times lim x to 0, 1 over cos x. What is that first piece? Yeah, this is 1, right? By our lemma from yesterday. This piece is 1 times. What is the limit as x goes to 0 of 1 over cos x?
1.
Yeah, it's also 1. It's 1 over the cosine of 0. This one we can get just by substitution. So this is 1 times 1 over 1, which is 1. Damn. Every now and then this document camera just decides to turn itself off. It realizes it's tired or something. I'm sorry. Let's initialize. Hurry up. There. Oh. Yeah. Yeah, it's true. The doc cam doesn't get much in the way of breaks. Okay. Oh, I'm not sure what it would eat. Questions on this first guy? So generally, if you see a trig limit that looks a little weird, like these, the goal is to somehow make use of the fact that we know the limit as x goes to 0 sine x over x is 1. That's generally the game. Let's see if we can do it for part B. That one looks a little trickier. So here we have lim t to 0 sine of 3t over 2t. And this kind of looks like sine x over x, right? If this was just sine t over t, that would be 1. But it's not. So here's how I would handle this. I would say that this is lim t to 0 sine of 3t over t times, I'll pop that 2 out over here. So this 2, I'm just bringing out here. Fractions multiply straight across. And then if I put a 3 up here and a 3 down here, something nice will happen. Because now the inside of the sine function upstairs here is the thing that's down here. And we can make a little substitution where we let, say, x be equal to 3t. And notice that as t goes to 0, x goes to 0 also. So I can rewrite this as lim x to 0 sine x over x times 3/2. So once you have the same thing down here as you have up here, you can make a little substitution like this, and that piece will be known, right? This piece is equal to 1. So this is 1 times 3/2, which is just 3/2. Problems like this, for whatever reason, used to be very popular in the calc teaching universe, but they're becoming less popular. I still think they're worth doing. So take a second, look at this, see if there's anything you'd like to ask. So here, like where did this 3/2 come from? Or here? Yeah, so what I've done here, I multiplied and divided by 3. I can make the algebra a little more explicit. So forget about the limit for a second. Let's just talk about the algebra. Sine 3t over 2t is the same as sine 3t over t times 1 over 2. And then that's the same as sine 3t over t times 3 over 3 times 1 over 2. And the 3 downstairs I bring inside. So that gives me the 3t downstairs. And the 3 upstairs I group with the 1/2. That gives me the 3/2. Yeah, the substitution is sneaky here. So because if you look at this expression, the only place the variable shows up, both times it shows up multiplied by 3, right? The only t's here are this one and this one. And each time it shows up, it's multiplied by 3. So that's the hint that you should substitute for 3t. Well, t here is a variable, remember, and we're sending t to 0. So we're looking at the limit as t goes to 0. So if you were to send t to 0 here, you would get x equals 0, right? In other words, as t goes to 0 in this expression, x is going to 3 times 0, which is also 0. So we don't need to know t's value necessarily. We just need to know what t is up to. What's he doing? He's walking towards 0. Okay, well, that means anything that's a constant multiple of him is also walking towards 0. So the way you actually saw me go through this is my preferred way to do that, where you pop the 2 out over here, and then you go, all right, what do I need to have up here to make the thing down here the same as the inside here? So once I have a 2 downstairs here, remember I left this blank, I just go, okay, well, I want a 3t because that's what I have inside here. So I better multiply by 3 upstairs and downstairs. The 3 downstairs gives me the thing I want. The 3 upstairs is to make sure I'm not changing the value of the expression. And then the trick to know to substitute is that the variable shows up each time multiplied by 3. This 3/2 doesn't matter. You can think of it as being inside the limit or outside the limit because constant multiples pop out of limits. So whether you want to think of it with parentheses like this or with parentheses like this, either way it would be the same. Personally, in this line, I'm thinking of it as being inside the limit, but it really doesn't matter because it's a constant. Those are good questions. Any other questions on this one? Okay, I'll say this about these sort of limits. Any sort of variation on these is handled the same way, right? We just have to find some way to make use of the fact that sine x over x goes to 1 as x goes to 0. So anytime you're given a kind of wonky looking trig limit like this, the trick is going to be to split it up and manipulate algebraically until you can use that sine x over x limit. Let's talk about the chain rule. Chain rule is one of the more important derivative rules we're going to cook up. There's a reason why this one isn't on the student teaching list. In Calc 3, you'll see a much expanded version of the chain rule for multivariable functions, and that kind of contextualizes things in a nice way that I wish I could share with you now. But let me just tell you what the rule is. This says if u is equal to u of x is a function of x, and both u and f are differentiable, then the derivative of the composite function f of u of x is found by differentiating the outer function whilst leaving the inner function alone. So we write that as f prime of u of x, and then multiplying by the derivative of the inner function. This is the way I usually write the chain rule. If you don't like the ddx out here, you can put a big prime here, right? That would say the same thing. So this is the nicest characterization that I'm aware of. There are other ways of writing this, and we can look at those a little later. But first, I just want to get you comfy with how the rule feels to use. So if you're trying to differentiate a function that has like an outer function and an inner function, these are composite functions, you differentiate the outer function while leaving the inside alone, and then multiply by the derivative of the inner function. Let's try an example. Find the derivative ddx of sine of x squared. So I'd like to ask, what's my outer and what is my inner?
The inner looks like it's x squared.
Yeah, definitely the inner function here is x squared. And the outer function is sine, right?
Yeah.
So if I'm going to differentiate this thing, I will differentiate the outer function, leaving the inner function alone.
Cosine s squared.
Very good. And then multiply by the derivative of the inner function. And I like to write these out schematically, right? Kind of one step at a time. So I differentiated the outer, leaving the inner alone, and then I multiply by the derivative of the inner. And then we can calculate. And so this is cosine of x squared times 2x. Not too bad, right? Let's try another. let's find the derivative d dx of the tangent of e to the x. So again, there's a clear outer and inner function here, right? Tangent is my outer, and e to the x is my inner. So I'm going to differentiate the outer function, leaving the inside alone. Derivative tangent is secant squared, and I leave the inside alone. And then I multiply this all by the derivative of that inner function. The derivative of e to the x is just e to the x. So this would be my derivative here. I'll do one more simple one like this before we look at more complicated stuff. How about e raised to the secant of x? Here, spotting your inner and outer is maybe a little tougher. What's the inner function in this last example?
is to secant x.
So e to the secant x is the whole thing, right? And the
Yes.
so the inner function here is just the secant x. Yeah, think of this as like e to the x, but instead of x, you've got secant of x. So my outer function here is the exponential. So if I differentiate e to some stuff, I get e to that stuff times the derivative of that stuff. And then the derivative of secant is secant tangent. So this is e to the secant x times secant x tangent x. We are actually to a place now where we could differentiate that big scary thing from the end of Nikita's lecture. We could. Now I'm not going to take us straight to something like that because that would be kind of terrifying. But we're going to ratchet it up slowly. You start combining all of these rules and you'd be surprised what you can manage. But first, I'd like to make sure we're all comfy with these sort of first three examples. Are there any questions on any of these guys?
I had one question.
Yeah, what's up?
How do I know when I'm at my final answer and that there's no more simplifying that I can do? Because every single time you get to the end of one of these, I'm like, wait, is there something more that I can do here? And I'm not sure how can I decisively know that, for example, secant squared e to the x times e to the x, that is as simple as it can get?
Well, let's see. That's not a bad question. I'll have to think about that for a second. These are kind of like algebra rules we're asking about, right? Can I simplify this? Well, remember, trig functions, you can think of them as like boxes you really can't pull things into or out of. So this is secant of e to the x times secant of e to the x. And there's really no pulling things in or out of the secant function. So there's not much I can do with that. And then e to the x is kind of also a primitive. There really isn't anything more we can do here either. So algebraically, I would say it's just a matter of asking, are there any like terms that you can combine? Are there any fractions you can put together? Anything like that? And for each of these, the answer is no. There's another question that I feel is kind of buried inside that question, which is like, when do you stop with the chain rule? Like, do I not need to now multiply by the derivative of this inner? And the answer there is, well, once you get down to an x, once x is your inner, its derivative is 1. So kind of two, when do I stop regarding the chain rule things? Algebraically, just, if there's nothing you can combine, if there are no like terms you can combine or anything like that, then you're good. In terms of the chain rule, when do you stop? You stop when your next level of inner function would be x itself. We'll look at that last one a little more closely in a second. All right, let's try something slightly more complicated. And I'll switch up the notation a little bit here. Find f prime of x, where f of x is the square root of 1 over x plus 1. And there's more than one way to attack this. But I think most people would identify the outer, at least written like this, as the square root function, and the inner as 1 over x plus 1.
The outer derivative is 1 over half multiple 1 over x plus 1 to the minus 1 over half.
Very good. So here's the derivative of the outer, leaving the inner alone, right? If I differentiate the square root is a 1/2 power. So I use the power rule. I bring down, come back here. This is 1 over x plus 1 all to the 1/2. So when you differentiate that outer function using the power rule, you bring the 1/2 down, and then you subtract 1 from that power. And we leave the inside alone during that process. And then we need to multiply by the derivative of 1 over x plus 1. And that 1 over x plus 1 derivative is something we would probably do with the quotient rule. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And you see how I'm doing this, right? At each step, I'm really only doing one thing. And whatever is left to do, I just write that out schematically with the primes. This is really what you want to do. You do not want to try to do it all in one go. So each new line that you write, you should really just be doing one thing. Like in this line, I differentiated the outer function. And I know I need to multiply by the derivative of the inner, but rather than trying to calculate that here, I just say, okay, it is whatever it is. It's the derivative of 1 over x plus 1. It's 1 over x plus 1 primed. And then in my next line, I'll worry about cleaning that up. Daniel asked an interesting question in chat. Why can't we just treat 1 over x plus 1 as its own number, bring the 1/2 down, and make the exponent 1/2? Well, when you look at this function, right? When you look at this guy, remember we're trying to think of these as composite functions. So let me remember what composite functions are from pre-calc. So this is like, I need 2 different letters besides F. This is G circ H of X, where G, the outer function, is the square root, and H, the inner function, is 1 over x plus 1. If you take this and plug it in here, which is what this says, then you get this. So H is the inner, the 1 over x plus 1 is the inner, and the outer is the square root. I'm plugging this function into this function to get this function.
Okay, I'm a little bit confused about this just because for the rest of them, it didn't feel like we were like plugging in the inner into the outer.
Well, it's not that we are plugging them in, it's that that's what this function is, right? This function is this function plugged into the square root function. That's how we identify the inner and the outer. That's what we mean by inner and outer, is that if you plug this into this, you get our function.
Okay.
So it's not that I've done any plugging in here, it's that whoever came up with this problem, in order to come up with this function, they plugged 1 over x plus 1 into the square root function. And that's what we mean by inner. So the thing that's on the inside of the outer function is something that has been plugged in to that outer function. Another way of saying, so let's finish the calculation and then I'll discuss some alternate notations. So this piece would be 1/2, and I'll leave this as 1 over x plus 1 to the negative 1/2. The derivative of 1 here is 0, so this is x plus 1 times 0 minus 1 times the derivative of x plus 1 is just 1. Downstairs here I have x plus 1 quantity squared. So I've got 1/2 times 1 over x plus 1 to the negative 1/2 multiplied by negative 1 over x plus 1 squared. And I suppose I should make clear that those are not being subtracted. And we can put all this into a single fraction if we want to. But maybe I won't. Maybe I'll just leave it like this for now. Let's not over confuse things. So another way to say this whole inner and outer thing this pen. Yeah, let me fresh place to have this discussion. So I'll leave this here for just a second and grab some fresh paper. So what do I mean by inner and outer? This guy can be thought of as the square root of u, where u is that inner function, 1 over 1 plus x. Right? This is the square root of something. What's the something? Oh, it's 1 over 1 plus x. So the square root is like your outer function, and the u, which is 1 over 1 plus x, is like your inner function. Does that feel a little more reasonable?
It's more easy to see visually.
Okay, good, good.
There were times in the past where we would use u to replace like a chunk of a function to just kind of look at it later. So that's
Yeah.
like almost familiar.
Yep, exactly. And that's precisely the intent here. Okay. I think the nicest next thing to do here is to show you where the quotient rule comes from. So using the chain rule, to prove the quotient rule. And this will also give you a way to avoid the quotient rule if you want. So first, let's look at something like 1 over g of x. And try to take its derivative. This is something I could jump into with the quotient rule. I could say it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Or I could think of this as d dx of g of x to the negative first power. And now my inner function is g of x, and my outer function is this negative first power. So this is something I could do with the chain rule. This would be -1 times g of x to the -2 times g prime of x by the chain rule. And if you clean this up, this is negative g prime of x over g of x squared. This is what you would get from the quotient rule.
Wait, how is it to the -2 power?
I'm using the power rule on the outer function.
Oh, okay, thank you.
Yeah, so when I differentiate this -1 power, he's going to come down, and then I'll subtract 1 from him, and -1 minus 1 is -2. All right, and if we applied the quotient rule, 1 over g of x, we said it, but let's go ahead and do it. This would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And since the derivative of 1 is 0, and the derivative of g is g primed, it really is the same thing. All right, this is negative g primed x over g of x squared. So whether you use the quotient rule or the chain rule on this 1 over expression, 1 over g of x, you get the same thing, you get this. Which hints at this idea that treating the downstairs as a -1 power can get us out of quotient rule stuff in general. So by the chain rule and product rule, I can prove now the quotient rule. d dx of f of x over g of x. Well, that's the same as d dx of f of x times 1 over g of x. Just algebra there. 1/3 is the same as 1 times 1/3, or 7/5 is the same as 7 times 1/5. Now by the product rule, this is the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. So that's f primed of x over g of x plus f of x times the derivative of 1 over g. We just calculated that using the chain rule up here, right? This is negative g primed over g of x squared. And then if you put those pieces together with a common denominator, See, we get exactly what we want. This way you can see both. So over here, I just used the chain rule, right? I never used the quotient rule, didn't touch it. That's the derivative of 1 over g, which is the piece that shows up here. So I can replace this by what we get from the chain rule, which is this. What do these look like? Let's write them both as single fractions. This is f prime over g. This minus I'll bring out front, minus f times g primed over g of x all squared. And then if you multiply by g over g, you get g of x times f primed of x minus f of x times g primed of x all over g of x squared, which is exactly the statement of the quotient rule. So a combination of chain rule and product rule can get you out of any quotient rule, which is a nice and true statement because the quotient rule is kind of a pain in the ass. Product rule ain't too bad. Chain rule ain't too bad. But the quotient rule, nobody likes the quotient rule. It's messy. It's up to you to decide which you want to use in any given situation. There are situations where I would use the quotient rule just because splitting the thing up and whatever is going to maybe be a little unpleasant, or because I know that the quotient rule thing for that expression is very nice. Maybe the square downstairs cancels a square root or something. But in a lot of situations, I would much rather use a combination of chain rule and product rule. So anything you could differentiate with the quotient rule, you could differentiate using a combination of chain and product rules instead. Specific things I would deal with this are like reciprocal functions, right? Anything of the form 1 over g of x, that we really don't want to mess around with the quotient rule there. It's just more work than it's worth. What would be a good example here? All right, so here's an example. I have a particle whose position at time t, it's moving along a straight line, its position at time t is 1 over the square root of 2t plus 1. And I want to find its velocity. Well, we know that the velocity is the derivative of the position, right? I'm looking for s primed here, that's all. No, Maxwell has not had breakfast. The cats have. So that means I need to take the derivative of, yeah, Maxwell is outside on the square root of 2t plus 1, like this.
Minus 1 over half.
Let's pause for just a second. So before we jump in, let's set up a strategy. You're correct. The first term is a -1/2, so don't stress. But I want to make sure everybody's on the same page with our strategy. Strategically here, we could treat this as a quotient, and you could differentiate this using the quotient rule. but the top is 1. The function upstairs is very, very simple. So maybe we don't need the quotient rule. Here's how I suggest handling this. I'm still writing my ddt out front because I haven't taken any derivatives yet. I'm just doing algebra. I would write this as 2t plus 1 all raised to the power of -1/2. This gets me out of doing any product or quotient rules. Now it's just a matter of the chain rule and the power rule. Now I'd way rather use those, right? The power rule is super simple. The chain rule is really not bad. I would do this 1,000 times before I differentiated it straight up with as a quotient with the quotient rule. And now, like Yiping was saying, the first term here, we have -1/2, that power coming down, times the inside left alone, and then I have to subtract 1 from that power, that's -3/2. So there's the derivative of the outer with the inner left alone, and then I have to multiply by the derivative of that inner. So here again, my inner function is the thing being raised to the power, and my outer is that power function. This is like u to the -1/2, where u is 2t plus 1.
Your 2t's plus 1 became 2t's minus 1.
Oh, thank you. Sorry. Yes, there we go. Okay. And now the only thing that remains to be done here is differentiating 2t plus 1. And his derivative is just 2. So this is -1/2 times 2t plus 1 to the -3/2 times 2. And this can be cleaned up a bit. So Sarah's question earlier, like, when do we stop? Well, everything here is being multiplied, right? This is -1/2 times this thing times 2. So the 2 times -1/2, those will eat each other up. This is -2t plus 1 to the -3/2. And I would be okay with you stopping here. But if you wanted to go further, you can call this -1 over the square root of 2t plus 1 all cubed. Okay, but either of these would also be acceptable. And I didn't have to touch a quotient rule, which is really nice. All right, we are just about out of time. In parting, let me show you an alternate notation that some people find appealing, and specifically, I promise your Calc 3 teacher will like. Some alternate notation for the chain rule. If y is equal to, how do we want to write this? F of u of x, same sort of thing. And here's some other ways we can write this. Dy dx, which is f primed, would be dy du times du dx. I think people like this because you can think of it like the du's cancel. If you wanted, you could write this as df dx equals df du times du. And again, the appeal here is that the differentials appear to cancel and give you, like, it's obvious, quote unquote, that those are equal to each other. But this is the derivative of the outer taken with respect to the inner. So this is the derivative of the outer with the inside left alone. And this is the derivative of the inner. I like, between these two, I prefer this one over this one. This one is a little bit more intuitive to me. So differentiate the outer function f, but not with respect to x, with respect to u, with respect to the inner function. So that means take the derivative of the outside, leaving the inside alone, and then multiply by the derivative of the inside taken with respect to x. Again, this notation, it's not a big deal for us here. There will be places where we use this notation, though, specifically when we get into related rates, right? Where your inner function is usually itself a function of time. This notation will be very useful there.
Is it this we'll learn in the Calc 3 class?
Yeah, so I'll show you the multivariable chain rule. What I'm about to show you is not something that you need for this class. But you can extend this chain rule pretty much arbitrarily. So here's what we've seen, right? Here's the kind of nice notation. But the multivariable version says if you have many functions, right? A function, say, of many variables, and each one of those variables is itself a function. This is a little bit too heady for us. The 3 variable case is here. Yeah. So if you've got a function with 2 independent variables, so instead of like y equals f of x, you have z equals f of x and y, where x and y are both functions, then you see that this notation is the nicer way to express the chain rule. The curly d's here mean partial derivative. That's something you'll learn about again in Calc 3. You don't need to stress about it for now. So for us, if you understand this and you understand the statement as we wrote it before, that like y prime here would be f prime of u of x u prime of x, right? Differentiate the outer, leave the inner alone, multiply by the derivative of the inner. Start with this, right? As you solve your problems, think of them like this. But then once you've gotten kind of comfy, see if you can couch them in this language also, because it'll be a useful tool for us when we get to related rates. Okay. Yep.
Is du derivative u?
Well, du on its own doesn't really have a meaning to us yet. Du dx, this is the derivative of u. So this piece right here, this is u primed of x, and this piece right here, this is f primed of u of x. That's sort of how those compare. And then the dy dx, that's y prime. So that's sort of the relationship between the two pieces. This piece would be the derivative of the outer with the inner left alone. And this piece is the derivative of the inner. Du and dx, dy, those sort of things on their own, like not as a fraction, but just du, they do have meaning. They're called differentials. And I will talk to you guys about differentials just before we get ready for test 2. That's one of the last sort of things we talk about in applications. A rigorous discussion of differentials is actually quite hard. You can look into differential geometry and the theory of differential forms if you want. I will give you just the very smallest taste of it when we get towards the end of chapter 4. All right, any other burning questions before I let you guys go for the day? Okay, let me take a quick look at what I have up for you in WebAssign. We have 7. So we need the trig derivative stuff and the chain rule homework stuff. There's some of that in the study guide, but I'll go ahead and post one small homework assignment for you guys, just a tiny little thing extra for you to work on to get more practice with the chain rule and the trig derivatives. Your test is next Wednesday, so I'll make that homework be due next Wednesday as well. So take a look on WebAssign. I'm going to give you one more thing because I think your other stuff, yeah, came due or is coming due on Monday and Wednesday of next week. So we'll deal with it like that. Alrighty. That's it from me, gang. I will see y'all on Monday.
Thank you for your class.
Of course, take care.